Hello, everybody. Good afternoon. Before I start, I want to thank everybody who came here because I understand it's already almost evening and it's the last talk for today, and I'm the only one who separates you from final for closing ceremony and after party. So I really appreciate your presence here, and I will try to do my best that you enjoy my talk. Yeah. So yes, I was introduced. I'm Elizaveta from both, and I'm a senior data scientist with focus on fraud domain. Apart from being passionate about machine learning and artificial intelligence, I'm really passionate about mountains. And I can tell you that actually there are some similarities between data science and mountaineering. And to illustrate that, let me share a quick story. So this summer, as usually, I went hiking in mountains. And I expected this beautiful views with snow, blue sky, and sun. I was very well prepared with equipment. I checked all weather forecasts. But then, on the first day, a huge thunderstorm hit us, and we were under heavy rain, strong wind, and even hail. And it doesn't matter how well I was prepared, still there was this weather external factor which I could not control. And I was standing there under the tree, hiding from hail. It reminded me that our recent projects with one of machine learning models which we had, where again, we were like very well prepared. We did extensive validations. We were sure that our changes to model will bring like positive impact to us. But reality was when we rolled out this in production, it almost failed, and we need to investigate why and fix the problems. So today, I will share this story about this model which we had and what we plan to do. I will change to you what I will share with you what happened in production and how we fixed it. And in the end of my talk, I will summarize some useful methods which you can use for you if you have something similar going on with machine learning models. So, as I'm part of fraud data science team, just one slide for you where I will explain what actually fraud is at both. And by fraud, I mean payment fraud at both. We usually deal with two main types, like failed payments and chargebacks. So failed payments is when we can't capture money from user bank account. So basically, user does a ride with like a boat, scooter, for example, but then we are not able to get money from them. Chargebacks, it's a bit of different story. It's example that some fraudsters steal cards, and then they are doing orders with these stolen cards. And when actual owner of this card sees this transaction on their bank account, they complain to bank that they haven't done these rights, and bank complain to us and we need to return this money. So this is a chargeback. So why I explain this to you? Because it related to change into idea which about the project I'm going to share. So we have a fraud predictor model. Basically, for all order requests, we predict if order is fraudulent or not. And it's machine learning model who does this prediction. And before, it was a binary classification model. So model returned two classes. Is it a fraud order or is it a good order? But we wanted to move from binary to multi-class classification model. So we wanted model to now predict three classes. It's a good orders, it's a failed payments, or is it chargebacks. Why we wanted to do this? Because with this more granular predictions, we can apply different business logic, and that's how we can optimize our fraud savings, so we can target fraud more precisely. So we had this idea in mind, and we did extensive historical validation where we compared our binary model to multi-class classification model. We used like 1 year of data to measure different metrics which we are interested in for different markets, and this historical validation showed very promising results. After that, we started to do silent live, where 1% of all order requests went to this new model. We ran it for 3 days. And also, what we saw in silent live, it actually confirmed our validation on historical data. So at that point of time, everything looked like perfect and ready for A/B testing, and we were so excited about it. So we started A/B test, where 50% of requests come to an old model and 50% of requests come to a new model. But we shut down this A/B test in 1.5 hours. We were shocked about it because it was like some surprises were going on, and we didn't expect of that to happen. So what was going on? Here is a plot, and you can see like blue line, it's aggregated model predictions by time. After test started. And dotted orange line, it's our average expected aggregated model predictions. And you see how it starts growing, growing, and growing. In the beginning, we thought, maybe it's some like hourly fluctuations. Okay, let's wait for this. We will not stop it right away. Then maybe it's some like daily fluctuations. Maybe it will go down, but it just increase, increase, increase. And when model predicts very high fraud prediction, we apply some actions to actual users. And one of action is that we send user to verification. So basically, we also started to see that we start to verify more and more users. And actually, probably most of them were good users. But verification creates a friction. So we decided to end the test and investigate what's going on. Here is another plot which shows you like silent life. You see that observed and expected values of model triggers, they kind of similar to each other across all these presented 4 cities. But during A/B test, actually expected and observed values, for some cities they were different like 3 times. It was quite a huge difference, and it only for like more than 1 hour. So, this happened despite we did all of our homework, and we need to investigate, okay, what is going on? We had several assumptions for the potential issues. And the first one that maybe it's some aggressive feedback effect from users on model predictions. So remember, I mentioned verification. And by feedback effect, I mean here that maybe users who were sent to verification, they just cancel verification and they start to order again. So they just kind of try to repeat and retry. And basically, they repeat, model again returns this like high probability. And that's how you would see this increase in average model predictions. Do you understand what I mean? Yeah, you're with me? Cool. But we checked it. There is some small feedback effect going on, but not even close to justify this like 3 times difference between expectation and observed values. So we had the next assumption, like maybe there is some model instability due to retraining. So between silent life and A/B test, we had 1 day, and during this day we decided to retrain model because we wanted for A/B test model to be as fresh as possible and to have all the information about fresh, recent fraud patterns if they which are in data. But that would require that labels of our data, like fraud and non-fraud, they should have a new trends. And we actually checked it, and there were no change in distribution of fraud labels between silent life and this like period of when model was retrained. So that was not an issue. Next assumption which we had that maybe some data issues in production. It was our main point of interest to investigate because our model, it has like lots of features, like around 90 different features about user behavior, payments, devices, and so on. So a lot of features, a lot of opportunities that something might go wrong. But also, it would mean that this actually, it need to break exactly on this day between silent mode and A/B testing. And it was actually hard to believe that something would break exactly on this date. So still kind of, we are not sure about this last point, but we decided to look more into features. To give you more details about our model, so our fraud predictor models, they are light GBM models. So if you heard about it, it's a type of gradient boosted trees model. And as I mentioned, it has a lot of different features. And to start with some kind of features, because we can't go one by one across all this many, we decided to start with the most important feature, and like for any decision tree-based model, you can just easily calculate feature importance, and we started from top of the list. And one of the feature was like an app version. It was very important for model. We started to dig into it more, and we actually noticed something. When we just developed a model, we expected this feature to be in this format like CI.21, where CI stands for iOS version, and 21 is a number of version of an app. But when we just started to look into version, we discovered actually a slightly different format. There is this .3 in the end. And we were actually surprised to see this because it happened that mobile team introduces changes without notifying us. Yeah, but kind of for them, it looked like some minor change, but in terms of model, it might mean a lot, because a version for our model, it's a categorical feature. And as you see, if we add this hotfix version, it means that we will have more categories for this feature. And the more categories, the more granular splits decision trees will do during model retraining, and it means that model may be overfitting on this data. So we found this. There was some similar case with another feature. We also fixed it. Basically, now we truncated this feature and we made it to be in our expected format. And then we checked, okay, is this changed model? How would it behave during our A/B test? So kind of we backtracked how this new model with this slight changes would behave during our A/B test in Silent Life. But it actually it didn't work. So we checked it, and there would be this, again, increase of trigger rates exactly when A/B test started. Next thing which we started to investigate, because previous one didn't work, model instability. Again, more technical details, how RGB model works. It returns you a score for each of your classes which you need to predict, but then you need somehow to translate the scores to labels. And for that, you need the classification threshold. There are different ways how you can define this threshold. Some people just hard-code it to 0.5, for example, but we use this false positive, true positive rates ratio on short data interval. So here is a bit of explanation how it works. So we have all data available, and then majority of data we use to train a model, but the last period we use to define a threshold. And to define a threshold, we compare these two lines of false positive rate and true positive rate, and where they intersect, it's an optimal ratio for us to define a threshold and to select a threshold. And okay, we kind of rethought this process, and we had an idea that maybe this data interval for defining threshold, maybe it's too short. Maybe there is some spike of fraudulent orders exactly on the day of this short interval, and it will make model more aggressive. And maybe that was the problem for us. So we changed this process, and we increased period of data where we define threshold, and also we updated the threshold selection itself. So now, instead of looking at FPR TPR ratio, we just fix model trigger rate, because we wanted to make model more stable. And kind of now we are just not looking at false positive rate, true positive rate. We're just looking into this trigger rate, how model would trigger, let's say 1%, and then select the threshold. Of course, it's not an ideal way, but actually it's more stable and more robust. And again, we added these changes, and then we wanted to see how this new model would perform during Silent Life and during A/B test. But again, kind of even this updated model, it would have this increase to trigger rates exactly when A/B test started. So nothing helps so far. What else we can do? During another round of analysis, we decided to look again more into features, and particularly in data drift. And we used this model, this method of built-in regression model to predict timestamp of model features. So if our actual fraud predictor model, we are using feature to predict fraud labels, fraud, non-fraud. But with this model, we use the same features, but to predict timestamp of this order labels. So basically, it would show to us if some features is very important to predict timestamp, it means that there is some data drift in this feature, and maybe it will give us a hint on which feature to look for. And actually it did. When we looked at feature importance of this regression model, one feature clearly was very important to predict the time. And then we just looked at average value of this feature over time. And you see, the thing which was hard to believe, it actually happened. So exactly on a day between when Silent Life finished and A/B test started, this value of this feature decreased dramatically and then started to have new distribution. It was a feature related to something like a number of connected users. It's a feature based on which is calculated using our graph database. For example, I'm connected to some other user using the same device. Basically, it just calculates connection of user IDs. Okay, we found out, and we started to talk to our engineers who is responsible for this feature. They said, okay, we didn't do any majority changes, what's going on, everything should be good, why you're asking for us? But as I mentioned, actually there were some refactoring happening for this feature. But it was a pull request reviewed, nothing should be broken there, but we showed them, okay, see the graph. And they actually found a bug in their code. So it was very unfortunate for us that it happened exactly on this day. But I mean, it's life and everything can happen. So we've talked with the team, they fixed the bug, and then again, all data was correct right now, and we decided to again retrain model and see how it would perform in Silent Life and during A/B test. And you see, now everything worked quite well, and this small bug caused us roughly 2 weeks of investigation and stopping our A/B test. So that was a story, but right now, let me share with you some other kind of general advice, which I would usually do if I see something going wrong with machine learning models in production. And yeah, the first thing is always to monitor data quality. Data drift is very important, and you can track it with this method of regression of feature on a timestamp, or there are some other statistical methods like k-divergent metric or KS statistics. So there are many different ways how you can identify data drift. Also, always compare your train and live data, and always be sure that your train and live data is identical. I remember a case at both, from several years ago. We had a model, and where one of the features was a distance. And we for model, we use this feature in kilometers. So range of this feature varies, let's say, from 1 to 50. But during serving, for some reason, backend started to send this feature in meters. And right now, instead of value of 2, model received value of 2,000. And you can imagine what happened there. Right now, I remember this a funny case, but back then we thought, okay, oh my God, how is possible? But we quickly defined it and fixed it. Another point about data quality, it's monotonicity of features. Especially with LightGBM model or XGBoost, you can easily set up monotonicity constraints, and I'm sure it's possible with other type of model as well. Monotonicity of feature, it means that if you think that there is a positive correlation between your feature and a label, you should observe it for your model. And if feature increase, prediction should not decrease in case of positive correlation. So you can easily set up some tests for that, and it's very easy to do, and don't remember about this point as well. Next thing which I usually do is to check model logs and to dig individual cases. On a first glance, it may seem that it's very kind of hard thing to do, and there are a lot of cases. But usually, we start looking from the weirdest examples or from some outliers, because it's actually like very important, and they can give you a hint on where the problem can be. So, another thing which is very important, which also have a lot of different funny cases we met, you need to be sure how your model predictions are used and how they affect final users. So, for example, let's say you are working on recommendation model, and you just started to working on that, but there are already some hard-coded kind of recommendations sent by backend to app, and it's some like top 5 places, for example. But then you develop your recommendation model, and you want that user will see not these hard-coded examples, but actually your model prediction. But it may happen that somebody just forgot to remove these hard-coded values, and actually it's not your model predictions which users see, but this like manual overrides from backend. Yeah, so it's also a very small thing, but you always need to check the flow of your model predictions, and you need to be sure that it's actually your model is used for user, but not some manual overrides. Last but not least, that you always need to be very careful if you have any kind of migrations going on. Migrations of your model pipelines or data platform. In the beginning of this year, at both, we migrated from Redshift to Delta Lake. And for us, data scientists, it meant that we need to rewrite our model queries from Redshift SQL to Spark SQL. For majority of models, it was okay, and we just rewrote it and checked everything was well. But for one model, data scientists launched A/B test, and after like a week, they noticed very strange metrics of during this A/B test, and they started to analyze, okay, how it's possible that we see such increase in like this GMV or number of order metric, and it took them a while to understand that actually just one SQL line was missing in model SQL for training data. And it was one line, but it meant a lot because it was very close with a very important filter for data. So this, after migration, model was trained basically on different data, and of course it produced different results. So always triple check if you have any migration processes. Here is all the summary of all the things which I just described. Remember about data quality, about checking model logs, about prediction users, and about checking migrations. So last but not least, if you want to remember just one thing from my talk, then remember that nothing of these methods which I just share will not help if you don't have a proper monitoring and alerting in place, because you'll just miss an issue. Why we notice so fast? Because we have dashboards in Grafana for many different metrics. We have alerting in Slack, and also we closely monitor what's going on. If we would not have it, we would just miss it, and our impact would be very much more larger compared to what it was. So remember, monitoring and alerting go first, and all the rest you'll be able to fix. And that's all from my side. Thank you.
Thanks so much, Elizaveta. It has been really full of great content, what you shared about your experience working in Bolt. And I'm sure we have some good questions for you as well, and Elizaveta is totally ready to tackle them. We have a lovely team here, handing you the mic. Here is, you just passed a really enthusiastic person who wants to ask the first question. Great.
First of all, thank you. Very interesting. And I wonder, you mentioned in your case that you had this issue after the Silent Life and then switching to A/B testing. How you dealt with the consequences, because these consequences cost the money, and if there are lots of false positives, then did you apply another kind of automation to solve that? So that's the question.
I mean, yeah, so there were not a big actually impact of like negative impact on the business because we've noticed it very quickly and we could stop this A/B test that it would not like cause us like millions of money lost. So impact was negative, but it was kind of negligible compared to like all other things which was going on. So in terms of money, but in terms of automation, what you mean?
I mean, if you have lots of false positives, and then out of those, you still need to detect those fraud ones, then will you rerun the previous model on top of that to fix the error?
I mean, if I understand your question correctly, so a false positive kind of, it's a totally different story. So of course we measure all this false positive impact, but it's kind of separated from what I just shared. Quickly on this, yeah, we are running another type of A/B test, but it's for not for this model, but globally for like to measure impact of fraud system, where we measure actually, okay, how we affect our business, blocking users, for example. What is like a impact of this user friction on GMV? But it's another type of experimentation which we are doing to measure this.
Thank you.
Awesome. Yeah, so a lot of questions. Great.
May I ask you, this one feature that changed because of the bug, why were you the only ones affected by that feature? Why was this feature buggy in the first place, and why didn't nobody else?
Probably we are not the only one affected by this because kind of our fraud system consists. There are machine learning models, but there are also fraud rules, and they're like using the same probably features, but they just didn't notice it. So probably they also are very affected by this, but for them they haven't noticed this effect at all. Yeah, but we did this model.
We have time for at least one more question. Now is your opportunity. Use it. Well, I see a hand. Yeah, so Sandra will come towards you with a mic.
Did you find out why this feature drift didn't affect the old model?
I mean, but so here I shared only like a metric for this like new model. I didn't share like this model trigger rates for the old model, and they actually also increased. So it affected the old one model as well, but in slightly less kind of way. Yeah.
And so maybe this is my wrong assumption, but why did the average number of connections going down increase the trigger rates? I would think it would do the opposite, but maybe my assumption is wrong.
Actually, good question. I mean, because it's not kind of a linear combination of kind of linear correlation between this feature and our labels, and usually like there are like dozens of other features, and given this like connection to other features, there was such a correlations going on.
We have time for one more question. And there is one.
Hello. My question is, what would have happened if the bug in production would have come several weeks or months later, once this new model was already in production?
Then model would start to produce this high predictions for many users, and then one case that we would do more like this kind of verifications for user because we predict that there are more fraudsters on our platform. But then some other kind of we would notice it anyway because, for example, we are fraud team, but there is a verification team, and they track like their metrics, and they would let us know. about it. And it's only one use case because there are some other business like action which we apply when we see when model predict gives high probability, and we would notice this as well on some other dashboards which we have.
We can actually take one more question. I see it. So a really quick one. In the middle somewhere there I saw a hand raising.
So yeah, I agree with a lot of the other questions that have come in, and mine is, are there any procedures to explain the model predictions currently with bots? Like, for example, if the model is going wrong, is it attributed to specific features? Do you guys have some system like that in place?
Okay, it's actually a very complex question. There are several parts. So first one is about model explainability, but then like about the model impact on business. And we looked at both of them. So we have dashboards, like more like a business-related dashboards where we track, okay, how much money model actually saves, or like what is a net impact of our models. But about model explainability, there are like several methods. For example, you can do like this feature importance, for example, or you can use Shapley values to understand what contributions of each feature for this particular prediction. And there are some like other ways as well, but we mostly use this too.
Thanks so much. Thank you, Elizaveta.
Thank you.